Okay, so I hope you all had a good break. So today we're going to do sort of the last. We're going to do the last part of the first half of the course. The course is basically divided into two sections, two kind of wildly different sections, although they connect up later at the end. The first section is just finishing up integral calculus and the sort of classical applications of integral calculus, finding surface areas, finding volumes, this sort of stuff. And then the second half of the course deals with sequences and series. I don't know if, how many of you have seen sequences and series before? Anybody? Somebody who's seen. So it's basically like if you, again, went back to elementary school and said, okay, you were thinking, well, I know how to add 2 numbers, I know how to add 3 numbers, I know how to add 100 numbers. Well, what if I start thinking about adding an infinite sequence of numbers, right? If I add 1 plus 1 minus a half plus a third minus a fourth plus a fifth plus minus a sixth, I start doing something like this. Can I still deal with those numbers in the same? Can I still deal with these sums in the same way that I deal with my regular sums? Can I cancel things out? Can I? What's legal and what's not legal? It turns out that some things that you do you think would be perfectly natural don't work at all, or will lead to craziness. Okay, so the whole second half of the course, starting from sometime this week, probably Wednesday or Friday, we'll be dealing with that. And once we get this idea of how to deal with infinite sums down, then we'll start thinking about how to take functions and then break them up into infinite combinations of simpler functions. So like, this is something that we hit on earlier in the course. Can you take a function and express it as an infinite polynomial, right? One thing that well, anyway, we'll see it soon enough. Okay. So functions can be expressed as polynomials. Well, polynomials or functions, are all functions polynomials? It turns out that in some sense, this is sort of true. Okay. Anyway, today we're going to do the last application of the first half of the course, and this is sort of introduction to what are called ordinary differential equations. Introduction to ordinary differential equations. Okay. Now, the ones that we're going to be dealing with are called separable ordinary differential equations. And in fact, we're going to be dealing with an even smaller category, first order separable ordinary differential equations. Okay. So we're throwing some adjectives. Okay, so again, let's start up with the definition. So a first order differential equation is basically an equation of the form y prime equals some function of x and y. Y prime equals some function of x and y. Okay, so this is probably not going to mean anything yet. Let me put up some examples of what we mean by that. So here's one example of a first order differential equation. Y prime equals negative 2 over xy plus 4x. Another example, y prime equals y minus 4x over x minus y. Okay, so you've got y prime, and on the right-hand side, you've got some function of x and y, right? This thing on the right here is some function involving x's and y's. Okay, some function involving x's and y's. Right? Another example, y prime equals negative x over y times e to the negative x. Okay, so you've got y prime, you've got, and you've got some relation forced on it. Okay. So it'll become clear in a second, but we're going to look for, we want to find something that satisfies the differential equation, right? A solution for the differential equation. So we'd like to find solutions where a solution of the sort of differential equation is a differentiable function that satisfies the equation on some interval. Right. A solution, yeah. We want to solve these differential equations. So we want to find some function y that satisfies the relation. Okay. So let me again. It's sort of strange. Like the formal definition almost doesn't mean anything until you see an example, and then the definition sort of becomes clear. So let me give an example for equation 1. So we'll give a solution to this guy here. If you take y to be x squared plus 1 over x squared, then y prime is going to be 2x plus negative 2 over x cubed. Right? Yep. Just differentiate it. You get this, right? 2x plus negative 2 over x cubed. Right? And then you'll see that we observe that negative 2 over x times y plus 4x, if we multiply that out, right, if you multiply that out, you see what you get y prime. Right? Multiply this out. Right? Negative 2 over x times negative 2 over x times y plus 4x actually equals y prime. Okay. So what does that tell you? That tells you that this function is a solution for this differential equation. Are the words becoming clear? Right? We have a differential equation. Differential equation is just some relation between y prime, y, and x. Right? And then you've got this thing, a solution. Solution is something that satisfies the differential equation. Right? You take this thing, you take y prime, and you see that y prime actually does equal negative 2 over xy plus 4x. Right? So this thing is a solution for this particular differential equation. Okay. And we want to solve differential equations. Okay, everyone all right? Just terminology at this point. Right. So you can think of this as you're trying to find a function, right? This y is a function of x, right? And you're looking for some function whose derivative satisfies this relation, right? Some function whose derivative satisfies this equation. That's one way of thinking about it. Another way of thinking about it graphically is that you're looking for a curve. So, so solution is a differentiable function that satisfies the equation, but you can also think of it as you're looking for, you want a curve in the plane that satisfies the relation. Right? You have this, you have the plane, the xy plane, so this is a way of visualizing it. You've got your xy plane, and you want some curve, you want some curve in the plane where the slope of the curve equals -2 over the x coordinate times the y coordinate plus 4 times the x coordinate. Okay, so you want the slope at every point to satisfy this relation, right? You want the slope to satisfy this relation. Okay, so even if without solving it, right? Even without solving it, you can look at this thing and get some information about what the slopes look like. Okay, you say, oh look, suppose I am at the point 1, 1. Well, if I'm at the point 1, 1, what should my slope be? Well, my slope is going to be -2 plus 4. My slope is going to be 2, right? So you say, okay, my slope is going to be 2 here. So I know that, I have a curve, the slope is 2 here, right? If I were at 1, 2, well, what would my slope be? Well, it'd be 0, right? I don't know, right? If I'm at this point 1, 2, well, y prime is going to be -2 times 2, that's -4, plus -4, that's 0, right? So I would know that the slope has to be 0. If I'm at this point, I have a slope of 0, right? And you could do this, now this would be really tedious, but you could do this at every single point, right? And then maybe, I don't know what it looks like, but maybe at every point you get some slope, right? You get what's called a slope field. Okay, and maybe it looks something like, who knows, right? So at every point you get some information about the slope, right? And that would actually give you information about, you could say, oh look, if I were here, then I would go here and then I'd connect to this guy, so like this, and then you get some sort of idea of what the curve actually looks like. Okay. Okay. So that's one sort of tedious computerized way that you get information about the solution. And then this is the sort of like the brain, the thinking way of getting solution. Like somehow you come up with a solution, say, oh, this is the solution, right? And then this would give you the curve. Y equals x squared plus 1 over x squared. Okay. Okay. But you can get these things, so you can get what's called a slope field, which gives one a sense of what are called integral curves. Okay. The integral curves, that's just the curve, the graph, the curve describing the solutions. Okay. This will, again, we'll do a simple example of this and it'll become clear in a second. Clearer in a second. Okay, everyone all right? Okay, so, so far we've defined, first order equations, we've defined a solution. We haven't defined the term separable. Okay, so here's the term separable. If, so you've got your first order, you've got your equation, y equals f of xy. So given the equation, your differential equation, y equals f of xy, if this f of xy can be split into a function of x times a function of y. That we call the differential equation separable. Separable. Okay, so I had an example, but I've just erased it. Y prime equals negative x over y e to the negative x. The third example that I put up there, well, that was separable because this function, this function can be written as, a function of x times a function of y. Right? Function of x times a function of y. So it's separable. Right? You can split it up into a function purely of x involving no y's, a function of y involving no x's. Okay, you're looking confused. Right? So here's your f, here's your y prime equals f of xy, right? Look, I can write this thing as that. Yeah. Maybe you just couldn't see it because the computer was in the way. Sit somewhere else. That's the solution. Okay. Okay. So here is sort of the prototypical example. When you start doing differential equations, this is the example that everybody does. Okay. So you have a population. P is the population. With a disease. So there's some sickness spreading through the population, okay, and this is the number of people that have that disease at that time. And t is time. So really, this p is a function of time. So the number of the population with the disease at time t. Okay, right. So this is these guys. This p and t are your y and your x. Okay, right. Y was actually a function of x. Although we just sort of hide it. We call it y rather than writing y of x all the time. Okay. But really, secretly, it's a function of t. Okay, so you make some assumption or observation about the disease. And the assumption is that the rate of change, the instantaneous rate of change of the disease is proportional to the number of people with the disease at the time. Okay, right? The rate of change is proportional of the diseased is proportional to the number ill. Right. So the more people that are ill, the faster the disease spreads. It's direct. It's proportional to that. Okay. And maybe that seems like a reasonable thing to say. Right. Rather than it's proportional to the square of the number of the people diseased. That would seem kind of strange, right? Where would that come from? Right? Why would a square be involved? Well, the number of people who are sick is going to cause the spread of the disease, right? Not the square of the number or the cube of the number, right? So this seems like a reasonable thing to say. So this is our differential equation, right? This is our differential equation. I want to say, what does P look like? Right? We want a solution. We want a solution for this because then we'll know how this disease is going to spread. So the technique that one uses is called separation of variables. Separation of variables. Questions? Somebody's whispering. Any questions? So separation of variables, the way you do it is you say, okay, I'm going to write this as the rate of change with respect to time is equal to k times t. Those of you who like esoteric symbols, there's an old-fashioned symbol that means is proportional to. It's sort of like an alpha. So if you write p prime is proportional to p, that's the same thing as saying that p prime is some number, some constant times p. Okay. In any case, you have your differential equation, right? And you do what's called separation of variables on it. So it's kind of weird, but you say move everything involving p to one side, move everything involving t to the other side. Okay, so you separate variables. It seems like a weird thing to do because you've been taught that this is not a fraction, right? So why is that okay? We'll explain why it's okay in a second. It's just a shorthand. It's just a shorthand for something that actually is legal. So don't worry, we're all right. Separate variables and then integrate. When you integrate this dp over p, what do you get? You get the natural log of the absolute value of p. Right? On the right-hand side, you're going to get kt plus c. Right? Which gives you the absolute value of p is e to the kt plus c. That's the same thing as let me move this up here. You get e to the kt plus c, but that's the same thing as e to the c, e to the kt. And what's up?
I think it's okay.
You okay? Okay. Okay, and I'm just going to replace this e to the c with some other c prime. Okay, because c is an arbitrary constant, right? E to the c is just going to be some arbitrary positive constant. I'm going to call that part positive constant. I'm going to call that guy c prime. Okay, so you get something like this. So this gives us information, and remember secretly this p is p of t, right? So this is what we have so far. Okay. That the absolute value of p is some constant times the exponential function. Okay. That your population looks something like the exponential function. Okay. This is the information we have so far. Okay. This is bad. Right? If you think about this disease, the spread is exponential, right? Which is bad. Or at least, I mean, unless this disease is a good thing. Okay. Everybody seeing this? Any questions so far? Okay. So, what was this thing that we were doing here, right? When we move the t to the other side and so on. Well, that seems wrong. If you were being proper about it, let's write the top thing here. P prime equals k p of t. So I'm going to write these guys as functions rather than suppressing the function. I'm going to divide both sides by p. Okay, and then I'm going to integrate both sides with respect to with respect to t. So integrate both sides with respect to t. Okay, that's legal, right? There's nothing fishy, nothing wrong with it. Okay, right? This is maybe fishy, but this is not, right? And then you basically get the same thing, right? You're going to get natural log of b of t equals kt plus c, and it goes on the same way. Okay, so the point is that although this was fishy, it was actually okay because it's just a shorthand for what's going on here. This is just a shorthand for this. Okay, if you want, you can do it this way. That's fine. Okay. I mean, this to me, I feel more secure doing something like this than this. But it's the same thing. So, okay. Okay, everybody all right? Yes?
I don't understand how e to the c becomes c prime.
Well, I'm just letting c prime be e to the c.
Oh, okay.
I'm creating a new arbitrary constant, c prime. What's c prime? C prime is e to the c.
Okay.
I'm just renaming it. Just renaming it. Okay. So now we have this absolute value. We have this absolute value on it, right? But let's think. What about the absolute value? Well, let's think. If we think about, so we said something like this, right? P prime is equal to k of pt, k times pt, right? Where k is some, I forgot to say, but k is some positive number, right? K is going to be some positive number. The disease doesn't decrease, the rate of change doesn't become negative, right? That would mean that the more people have the disease, the faster you don't have the spread, right? It would be strange, right? Okay, so k is positive. Okay, so let's think about the slope field. What does the slope field look like? Well, this is t and this is p, right? Our x and y. So what does the slope field look like? Well, if, right, suppose we're here at, it's some number times p, right? It's some number times the y coordinate, right? So it's just going to be, let's pretend, just to make things simple, that k is equal to 1. Okay. Then at 1, 1, what's the slope going to be? Set 1. 1. Thank you. Right? Like when p is equal to 1, the slope is going to be 1. So all along here, the slope is 1. Right? All along here, the slope is 2. All along here, the slope is 3. Right? As you get higher up, the slope increases. Right? The slope increases by 1 as you step up 1. Okay? So what does that tell you? Right here, the slope is going to be a half. Right? As you get closer, it's going to be a quarter. Right? Okay. What does that tell you? Well, that tells you that your p is never going to become negative. Right? Your population starts off non-negative. Right? You don't have a negative population. Your population starts off non-negative, and right, as time goes on, well, it just starts going up. Right? The slope is positive. The p is going to increase. Right? So this p is actually always positive. So we can get rid of this. I guess we could have just said, look, it's a population, so it's always going to be positive. Right? So not a negative number. But you can see it mathematically from here. Okay. Okay. So what do you get? Right? That p of t, is going to be some constant times e to the kt. Right? That's what your solution looks like. This is what your solutions to the equation look like. That's okay? Okay. So, yes, Anna?
So why in the first one it was C prime and in the second one is just C?
I'm sorry, I just renamed it again.
Okay.
Mathematicians tend to use C as any constant, and it's not necessarily the same constant. So in a book, you probably see something like this. You see either the C and then you see a different C, but this C is not the same as that C. This C is actually either the previous C.
Okay.
Yeah, I'm sorry. Let me call it C prime, just to make it clear. But I should say that in math books, almost always the C is some fixed but constant that is not necessarily the same one as the previous. Okay. So this is kind of cool, right? Because you say we just started from one assumption that the rate of this change, the rate of the spread, is proportional to the number infected. Right? That's the only assumption we made. And from there, we get this conclusion that you have to be the exponential function. Right? You have to be some multiple of the exponential function. Okay, that's kind of amazing, right? That's the only thing that's going to happen. Right? Okay, based on that assumption. Okay, so this is what differential equations is about. You're trying to learn something about something that's happening, and you say, okay, I understand that you make some observation about it, and see what that observation forces the function to be, forces the solution to be. Right? Now, I talked to a biologist about this. I said, well, how do you guys, it seems strange to me that you can use differential equations. And he said, well, we get the solutions, and we don't assume that this is exactly what happens, but we say that we can learn sort of properties of what's going to happen. Right? So maybe this isn't exactly what's going to happen, but you know that the spread is going to be something like exponential. Right? Okay. Second example, mice and owls. So this one, you have some mice. This guy is the number of mice, and you have an owl population. The owls are preying on the mice. Okay, so we make some assumption or make some observation that. So this, if I say something like this, the rate of change is the rate of growth of the population, the mouse population is like one-half the growth of one-half the population at that time. What that's modeling is just the growth of the mouse population. Okay, right? This would again end up as an exponential function, right? The mouse population is booming, right? Is exploding, right? But we're going to throw in something, which is that the owls take off 450 mice, every year. Okay, so there's for some reason like a fixed population of owls, and they always kill the same number of mice every year. Okay. So I usually rename this as the Danes and Grendel. Because that sort of makes more sense to me. Like Grendel, Beowulf, Grendel the monster. Right? Because if you say something like this is sort of saying that the owl population is constant and they always take the same number, right? That reminds me a lot of Beowulf, Grendel and the Danes. Grendel always takes 12 of the Danes every night for 30 years or something like that. Anyway, anyway, I don't know. I think that's better. Anyway, so this is the number of days. In any case, it's called a predator-prey model. So, so you say, okay, well, this is the same thing as. Let me rewrite this like this. Right, so I've got p prime equals p of t minus 900 over 2. Right, and So take a minute and do a separation of variables on this and see what happens. See what you can get. Just turn to somebody nearby. We'll do most of this together. Turn to somebody nearby and tell them how you started it on. Okay, so somebody tell me what to do. Tell me what to do. Kristen, how about you? So you do separation of variables.
Yes. I honestly, I have no idea. I'm sorry.
That's all right. So we'll do basically the same thing that we did last time. We'll divide both sides by this thing to bring it over to the left. Okay. So we'll say like this. Okay. And then we will integrate both sides with respect to t. And the same sort of thing happens, right? You get natural log of the absolute value of this equals 1/2 t plus a constant, which gives you that the absolute value of this equals some constant e to the t over 2. And that those c's are not the same, okay? Same thing. Franklin, what's up? Okay. Right. You've got the derivative of the bottom, right? The derivative, you've got the derivative over the function itself, right? So, right, you've got du over u, that's going to be, right, that's going to be natural log of the absolute value of the bottom, right? Integrating over here, you're going to get 1/2 t plus constant, right? Then we take e to both sides, e to both sides, and we end up just like last one. It's okay. 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 Now, at this point, let's think about the absolute values again. If we look at the slope field, we see that as long as p is bigger than 900, well, what happens at p equals 900? Well, p prime is going to be 0, right? So that tells you that at 900, the slopes are always 0. Yeah. So you actually know what's going to happen in some sense, right? If the Danes had 900 people to start off with, that's perfect, right? They multiply so quickly that it sort of evens out, right? The number of people that get produced is exactly the same as the number of people that get killed, and just stays stable, right? They exist in harmony, some sort of harmony, forever. Awful, some sort of awful harmony forever. Right? Now, if p is bigger than 900, right, you see that the slope is always positive, right? The slope is always going to be, right, if it's 901, then the slope is a half. Right? If it's 902, then the slope is 1. Right? And on the other side, if you're less than 900 by 1, then your slope is negative a half, becomes negative 1 at 898, right? And so on and so forth. Right? Okay. So what you see is that if p is bigger than 900, it's always going to be bigger than 900. If p is less than 900, it's always going to be less than 900, right? Because you see what's going to happen. It's going to increase, or they're going to go to 0. Okay. So it's either always bigger than 900 or always less than 900. So this term here is either always positive or always negative, right? P of t minus 900 is either always positive, right? If I'm writing one of these integral curves, it's always going to be positive, or it's always going to be negative, right? It doesn't go back and forth, right? So I'm going to just subsume that. I'm going to write that as P of t minus 900 is some new constant c, right? dt over 2. So this new constant c is either, plus c, plus, let me call this c prime to make it clear. It's either plus c or it's minus c, right? If p of t minus 900 is negative, I'm going to call it, it would be negative c, right? It would be minus 1 times c. If it's positive, it would be plus 1 times c. Okay, so I subsume the plus 1 or minus 1 into the constant. Okay, so this constant could be positive or a negative, unlike the previous one. Yes?
Could we also have done like plus 4 factors for both sides and just divide like 18? So like another way of doing it without 2 minus like that.
Yes. Yes, I think that also. Okay. Okay. So what happens is you get that P of t is 900 plus c prime e to the t over 2. So that would that's the solution for your this is what the solutions look like, right? This is what the solutions look like for your equation. Okay, like these are the only possibilities for the Dane population. Okay. If you knew, let me just say one last thing before you go. If you knew that the initial population were 901, if you knew that the initial population were 901, what would that tell you? Well, that would say that 901 is 900 plus C prime, oops, plus C prime. Right? So that would tell you that C prime, of course, is 1. Right? So, and if you knew that the initial population were 900, then that would tell you that C prime is equal to 0, right? So having an initial condition, this is what's called an initial condition. So initial condition. An initial condition. Having an initial condition specifies which of these curves we're writing on. Okay, and says, okay, we know exactly what solution we're taking. Okay, right? If it was 901, then we see that the Dane population ultimately, heads off towards infinity, and that's wonderful, right? Or if we see if it's less than 900, they die very soon. Right? They get eaten off soon. So having the differential equation gives you a whole family of possible solutions. And then having an initial condition will specify which one of the solutions you're using. Okay, that's it for today. We'll do more of this stuff next time. And then after that,